Okay, before we do the next problem, I want to give you some suggestions, and just basically a rehash of what we did in problem 1, example 1, suggestions for solving related rate problems. And step 1 is to sketch a figure if at all helpful, and particularly if it's a geometric situation. So step 2 is to identify and label all of the variable components in our sketch, or whether or not we have a sketch. That is, the components that are changing with time. Now, we may have some components that are constant or a fixed amount. For instance, maybe we have a ladder sliding down a wall. Well, of course, that ladder is a fixed amount, and we would label that. That's not going to change with time. But the distance the foot of the ladder is from the wall, and the distance the top of the ladder is from the ground, that would be something that would be variable amounts, wouldn't it? Well, the third step is to first decide what rates are given and what rates are to be found, and express those rates in terms of derivative with respect to time. You saw that we did that in the previous example. And the fourth step is to find, once we've identified the variables that we've got rates about, okay, then we're looking for an equation that connects those variables, not the rates, but the variables. We'll use that equation in a moment to find the connection between the rates, but we're looking for an equation that involves just the regular variables. So step 5 is to implicitly differentiate the equation that we found in step 4. And what this will do is we'll produce an equation relating the rates, that is, relating the given rates with the rate that we are to find. And once we have that equation, then we can actually find the rate by substituting those values, the appropriate values in. In fact, that's what step 6 is. Take the equation that we now have from step 5 and substitute all the given values. That's all the given rates and the specific variable values that we're freezing at into that equation. And then after we do that, if we don't already have it solved for the given rate, then that's what step 7 is. Solve for the derivative that will give the unknown rate. Solve for the derivative that will give the unknown rate. Okay. Well, let me turn to the next page and set up. Okay, here's our problem. We have a 26-foot ladder that's placed against a wall. If the bottom of the ladder is being slid from the wall at a constant rate of 2 feet per second, at what rate is the top of the ladder moving down the wall when the top of the ladder is 10 feet from the ground? Well, let me make a statement here. Intuition would lead us to believe that since the ladder is a constant length, that the top of the ladder will move down the wall at the very same rate as the bottom of the ladder is moving away from the wall. But this is not the case. And so you have to really be careful with just using your gut instinct or your intuition. Because it will lead you astray many times, and we'll see that as we're solving this problem. Okay, well let's draw our diagram. Remember, that was our step 1. So we've got this wall, and we've got a ladder propped against the wall. Okay, let's make this a ladder. Okay. Now, what's changing, see, the distance that the ladder is from the wall, that distance, that's changing, isn't it? Because the ladder is moving away from the wall at the bottom, and of course the distance the top of the ladder is from the ground is also changing. And so those are the variables that I need to label, and I'll just call this amount x and this amount y. Now that's the x is the distance the bottom of the ladder is from the wall, and y is the distance the top of the ladder is from the ground. Now this ladder is 26 feet tall, isn't it? Okay, or 26 feet long. And so that's something that's not changing, and it's all right to put that value in there. But we're not going to put the 10 feet in there, 10 feet from the ground in there yet, because that's a variable, that's the y variable's value at a particular time, and we've got to keep thinking about this as a dynamic situation before we fix the time. Okay, now what was the second thing that we do? Oh, what is the given rate? And now what we're actually doing is we're going to put together what's given to us and also our diagram. And so what we're told is that the bottom of the ladder is being slid from the wall at 2 feet per second. So that means that distance x is what's changing, isn't it? We're sliding that, and so that's the rate of change of x, okay, the distance from the bottom of the ladder to the wall. So that's what's given to us. Derivative of x with respect to t, we're told, is 2 feet per second. Let's put that in here just to keep track of it. Now, what is it we're supposed to find? Okay, well, we're supposed to find, let's see, at what rate is the top of the ladder moving down the wall? Well, the top of the, so we're actually talking about what rate is the distance y. What's the rate of the distance y changing? What's that rate of change? Because y represents the distance from the top of the ladder to the ground. And so what we're asked to find is the derivative of y with respect to t. And specifically, and we'll use this later on, but specifically when y has what value? Oh, when y is actually 10 feet, because we want to know the rate of change of y when y is 10 feet, or when the top of the ladder is 10 feet from the ground. So we have two variables, x and y. We need an equation. That's the next thing we do, is we need an equation relating x and y. Those are the two rates that we need to, those are the rates that we need to know about, but we need an equation that involves the variables x and y. And that ought to be a pretty easy equation for us. We're going to assume, of course, that this wall is at a right angle with the ground, and so we could use the Pythagorean theorem, couldn't we? We basically have a right triangle where 26 is the hypotenuse. And so the equation that would relate these two variables, x and y, would be x squared plus y squared is equal to 26 squared. And that ends up being x squared plus y squared is equal to 676 is what 26 squared is. Okay, so we have our diagram, we have the two rates, we have an equation, the two rates that we have information about and what we're supposed to find, and we have an equation involving the two variables that are in those rates. But next we need an equation that relates the rates. So then to do that, we now find, we take the implicitly derivative, we implicitly, bad choice of words. We use implicit differentiation on the equation above. So we're going to, but with respect to t. So we're going to take the derivative with respect to t on both sides of this equation. Sorry it took me so long to spit that out. Well, on the left side, the derivative of x squared with respect to t will be 2x times the derivative of x with respect to t. And the derivative of y squared with respect to t will be 2 times y times the derivative of y with respect to t. That's a y. And of course, the derivative of a constant with respect to any variable is always 0. Okay, so there's the information we are given now. Okay, now here's after we do this, then we begin to substitute the values. Remember, that was the next step. This is a problem a little different than the first one. Now, let's keep in mind the information we have here. See, we are supposed to find, let's keep this in mind, we're supposed to find the derivative of y with respect to t when y is equal to 10. Now we're ready to use that. And we already know that the derivative of x with respect to t is 2. And so we can take this equation and put the information in we know. So we can say 2 times, we don't know x, do we? 2 times x times the derivative of y with respect to t, which is 2, plus 2 times y, but we know in this case y is 10, times the derivative of y with respect to t is equal to 0. Now, here's the issue. This is what we're trying to find. But to find it, we need this value. And so now the question ends up being, what is x when y is 10? Because we've got to know the x value to put in here because we're trying to create this idea when y is 10. So we have to use this equation one more time. In fact, before we do this, let's clean this equation up just a bit, and let's say this is 4x plus 20 times the derivative of y with respect to t is equal to 0. And if we can figure out what x is, then we'll be close to solving, won't we? So what we're going to do is go back, though, to this idea that we have, okay, of a right triangle. And the ladder is 26 feet long all the time, but now we're fixed at a position temporarily to find out what x is. See, the y value is 10, so what is x? Well, remember, we have x squared plus 10 squared in this case is equal to 26 squared, where that's x squared plus 100 is equal to 676, or x squared is equal to what, 576? And so x is the square root of 576, okay, which is, actually it's not approximately, it's actually equal to 24 feet. So when the top of the ladder is 10 feet from the ground, then the bottom of the ladder is actually 24 feet from the wall. Okay, now that we have this, and we have this, we put these two pieces together to finish off the problem, because we would have 4 times our x value now, plus 20 times our derivative of y with respect to t is equal to 0, and then we would just begin to solve. Okay, and so what's 4 times 24? 96. So we end up with 96 plus 20 times the derivative of y with respect to t is equal to 0. Let's subtract 96 on both sides. So we'd have 20 times dy dt is equal to negative 96. Then we'd divide on both sides by 20. And we would end up with a negative 4.8. Now, let's pause here. Oh, what does this mean? Approximately. I don't. Yeah, actually, it's exactly negative 4.8. Well, here's the first thing that we need to realize is when we came back up here, when we talked about this given rate that we started with. See, if we look at that x value is getting bigger, isn't it? When we start pulling that ladder away from the wall, that x value is increasing, getting bigger. And so the rate of change of x would be a positive amount because that is increasing. Now, on the other hand, y is getting smaller, isn't it? And so that's the reason we have the rate of change as a negative value. Now, in terms of answering the question, we would answer it as a positive value, but that's the reason that rate of change for y came up as a negative amount. So here's here's our answer. I'm kind of cramming it in here. And it's because of the result we got here, the top of the ladder is moving down the wall at a rate of 4.8 feet per second. Okay, when the bottom is 10 feet from the wall. So I've run out of room. I bet you can't see that. So we go back to that, yes, it's moving down the wall much more rapidly than it's moving away from the wall at this point. In fact, if the ladder was only 5 feet from the ground, the top, then it would be moving down the wall much more rapidly. Anyone that's been on a ladder that's begun to start sliding will understand that completely. Well, that ends example 2. We'll prepare to do example 3. Actually, I wasn't finished with example 2 because I wanted to point out once again that we had to use this equation right here in more than one way, didn't we? This x squared plus y squared is equal to 26 squared. We actually used it again here. We used it to find the relationship. See, we used it at this stage right here to find the relationship between the rates. And after we had the relationship between the rates, then we had to use it to find actually a value of x when we knew the value of y. But we did this part. This is first, and this was second. That is, we don't use any variable amounts until we have the equation relating the rates. Okay, example 3. We have a spherical balloon that's being inflated at a rate of 5 cubic feet per minute. At what rate is the diameter increasing? Oh my goodness, I've butchered this, haven't I? When the diameter is 12 feet. I'm sorry for all the smudges there. I don't think really a diagram is going to help me a lot here. So I'm going to just start it right in and say, okay, what is known? And usually that has to do with rates, doesn't it? What is known? And we need to write what is known, right in calculus terms. That's what we were talking about before. And calculus terms means what? As a derivative. Okay, so what is known here is the rate at which the balloon is being inflated. And that's actually telling us what the rate of the volume is changing. We're putting 5 cubic feet of air every minute into this balloon, or whatever is being put into it, air, helium, whatever. But we're increasing the volume by 5 cubic feet per minute. So what's given to us is the rate of change of volume with respect to T. That is the 5. And of course that's cubic feet per minute. So V represents volume. That's what's given to us. Okay, well, what is it we're supposed to find? What to find? And of course, in terms of rates. In terms of rates. Well, we're supposed to find the rate at which the diameter is increasing. So actually we are finding the rate of change of the diameter. And I'll say D, where that's going to represent diameter. That's what we're asked to find. So that is, we're going to find the derivative of d with respect to t. That's what we're supposed to find, okay? And specifically, though, what? When d is equal to 12 feet. Okay, so we look above, and we've got two different variables, v and d. We need an equation with v and d. Okay, that's the next issue now. Well, of course, v represents volume, and d is the diameter, and we're talking about a sphere, and so we need to use the equation for the volume of a sphere. Now, unlike the problems that we've done before, okay, where, for instance, we had the area of a circle, I expect you to know the area of the circle, but I don't particularly expect you to recall the volume of a sphere. And so if you were to need this on a test, then I would give it to you. If you're doing something for homework that's not given to you, you have the resources to find this out. Okay, the volume of the sphere is given by v is equal to 4/3 times pi r cubed, where r is the radius. Now, we need an equation that has v and d in it, not v and r. So let's make a note, of course, it's not too hard to figure out, that d, diameter, is just 2 times the radius, isn't it? So that would tell us that we could replace the radius. We solve for radius here. Radius would be what? D divided by 2? So we could replace r with d divided by 2, and then we would have such an equation. So that gives us now this volume equation is going to look like v is equal to 4/3 pi times, instead of r, d divided by 2, but that's cubed. And so that will be v is equal to 4/3 pi times d cubed over 8. And then we would simplify that. You know, the 4 over 8 will be 1 over 2, so we'll actually end up with what? 1/6 times pi times d cubed. Okay, so now we finally have that equation that involves v and d. And now we need to do implicit differentiation. On that equation. So we'll take the derivative of both sides with respect to t. So the derivative of the left side is just derivative of v with respect to t. Okay? I mean, actually, let's write it this way. We're taking the derivative of the left side, which is just v, and we're taking the derivative of the right side, which is 1/6 pi times d cubed. Okay? Now, of course, the left side we'll just rewrite as dv dt. And on the right side, what we have is the constant 1/6 times pi. Okay, so that's just a constant. And we have to find the derivative of d cubed with respect to t. Well, remember that d is like parentheses with t stuff inside of it. So we bring the 3 down, decrease the power by 1, so it's 3d squared. But then we have to multiply with the derivative of d. Okay, so as we simplify all of this, let's see where we are. Okay, we have dv dt, and 3 times 1/6 is 1/2, isn't it? And pi times 1/2 is pi over 2. So we end up with pi over 2 times d squared times d derivative of diameter with respect to t, dd dt. Okay. Okay. Well, we're getting close now, and rather than go to the next page, let's just kind of turn this on the side here. Let's I apologize for this, but let's move this over here. And I wouldn't want you to do it this way. But what is it we're trying to find? Oh, we're trying to find the rate of change. That's what we're trying to find, isn't it? See, that's what we decided way up here. That's what we need to find. So, and let's recall, let's kind of put our pieces together now. Recall that we know the derivative of v with respect to t is the constant 5, don't we? And we want to know the derivative of the diameter, or the rate of change of the diameter, specifically when the diameter is 12 feet. So we put that information in to the left side of the equation. dv dt we replace with 5, and we have pi over 2 times our d value squared times the derivative of d with respect to t. And remember, this is what we're trying to solve for. And so we just need to do a few calculations here. And so what we end up with, of course, 12 squared is 144. So we get 144 here times the derivative of d with respect to t. And that ends up being 72 pi. So we have 5 is equal to 72 pi. I mean, it's 1/2 times 144, which is 72, times the derivative of d with respect to t, isn't it? And so we would divide both sides by 72 pi to calculate our rate of change. So we'd have 5 divided by 72 pi, and that's approximately 0.022 feet. Remember, this is a rate of change of diameter, okay? And so rate of change is 0.022 feet per minute. That's the rate, the time units that we're talking about. So when we get to a big radius, then that diameter is not changing very much, is it? That's a pretty interesting idea. Okay, there's our result, 0.22. Man, that's, what is that, 22 1,000ths of a foot? That's not very much in a whole minute, but we're talking about a very big balloon at this point, aren't we? Well, that's the end of example 3. I think I've got one more example I want to do, and then I'll set you loose on doing your homework. Okay, here's our example 4. We have an airplane that's flying at an altitude of 6 miles, and it's on a path that will take it directly over a radar station. If the distance from the plane to the radar station is decreasing at a rate of 400 miles per hour when the distance between the plane and the radar station is 10 miles, what is the speed of the plane at that time? So here's the idea. Here's the radar station, and say here's the plane, okay? And we'll say the plane is flying in this direction, okay? And we know that the plane, I'll go ahead and do it this way, we know that that plane, it will assume is traveling at a constant rate of speed, at a constant altitude, so we know that that altitude is 6 miles, okay? Now, this side, of course, is not changing, but as the plane, remember the plane is flying in this direction, isn't it? And so this distance this is the distance from the plane to being directly over the radar station, and I'll call this distance y, the actual air distance between the radar station and the plane. Now, we have to be careful about being confused here, because remember, well, let's talk about what's given, okay? What information do we have that's given to us? And what we're given is the rate of change between the plane and the radar station. And what I'm claiming is that rate of change is dy dt. See, that's the way a radar station works, isn't it? That it sends a signal to the plane. So it's not going horizontally, it's going directly from the radar station here to the plane here. And so it's that rate of change that's the 400 miles per hour. Now I'm going to throw in another little twist here, because that y value is getting smaller as the plane travels to be more and more directly over the radar station. So it actually should be a negative 400 for our rate of change there. Okay, and if we didn't put negative, well, don't worry about it. We'd come up with something that we'd interpret later on correctly anyway. Now, what is it we're supposed to find? We're supposed to find the speed of the plane. But the speed, remember, speed is nothing more than a rate of change of a distance. And so in this case, what we're really needing to find is dx dt. That's what we need to find, okay? And we need to find it specifically when y is 10 miles. See, and that's what it says, when the distance between the plane and the radar station is 10 miles. And we're not talking about a ground distance, we're talking about a distance through the air. And so it's specifically when y is 10. Okay, so now we need an equation with x and y, don't we? And we can rely on the Pythagorean theorem again. What we would know here, y is the hypotenuse in this case. And so our equation would end up being x squared plus the square of the legs. So one leg is x, the other is 6. X squared plus 6 squared is equal to the hypotenuse squared. And the hypotenuse is y in this case. And so that certainly ends up just being what, x squared plus 36 is equal to y squared. Now, we implicitly differentiate, don't we? Implicit differentiation is the next thing we do on that equation. With respect to t. So that would say that when we take the derivative, of course, of x squared, we get 2x times the derivative of x with respect to t. When we take the derivative of 36, which is a constant, we just get 0. And when we take the derivative of y squared with respect to t, we'll get 2y times the derivative of y with respect to t. And I just didn't go through all those details. Now, what is it we're trying to find? Oh, this is what we're trying to find, isn't it? So we could easily solve for that before we get very far by dividing each side. Of course, that plus 0 we can ignore, can't we? By dividing each side by 2x. So we would end up with 2y divided by 2x times the derivative of y with respect to t. And of course the 2's will cancel there, and so we simply end up with derivative of x with respect to t is equal to y divided by x times dy dx. Now, we've got a little bit of an issue, I think. Let's see. What information do we have? Well, we're specifically know that derivative of y with respect to t is negative 400. And we know that the derivative of, and we know that y, we need to know this when y is specifically what, 10 miles? But we still need to know the x value, don't we? See, we can fill in the dy dt, my bad. We can fill in the dy dt and we can fill in the y, but we need to know the x value. So we come back over here to our diagram, and what we're wanting to know is the value of x. See, this is the value of x specifically when y is 10, and that altitude is always 6. So we solve for x by using the Pythagorean theorem again. We have x squared plus 6 squared is equal to 10 squared. And I mean, that's, again, just the Pythagorean theorem. And we go through this, and we would end up with x is equal to 8. Now, you could figure that out pretty easily. So now we have that x value to complete, don't we? So the derivative of x with respect to t is y, 10, divided by x, 8, times dy dt, which is 400. And just a little bit of calculation. Oh, and it's actually negative 400, isn't it? So a little bit of calculation here, and that comes up to be negative 500 miles per hour. Now, we have this issue again. The reason that this is negative is because x is actually getting smaller. We're flying toward the radar station. But to answer our question, we would ignore that negative, wouldn't we? We would say the speed of the plane is simply 500 miles per hour. Okay, well, that ends our examples for related rates. Obviously, I can't show you everything that you might run into, but I hope this gives you a good foundation so that you can be successful in all of your problems.